Yeah. The 7 big ideas behind the DB2 emergence, or which the big ideas which led to the existence of DB2 BLU. These are, the number one is simple to implement and use. IBM has made DB2 BLU very easy to use. We don't need dozens of parameter controls. We don't need software system. We don't need exotic hardware. We don't need secondary servers. So we can make use of DB2 BLU with our old existing hardware. Whenever we talk about the administration of DB2 BLU, we discuss more about what we don't need to do rather than what we need to do. We don't need physical design tuning. Operational memory and storage attributes are automatically triggered. We don't want to spend time in creating indexes, creating entities, dimensioning data using multidimensional clustering data, distributing data with partitioning key, providing optimizer hints, retrieving space, collecting statistics, and much more. A lot of things have been automated in DB2 BLU. It has the ease of just load the data and fire the query and enjoy performance gains. That's it. And one of the reasons it is easy to use is it uses the same DB2 process model, same storage construct, same buffer pools, same SQL language interfaces, same administration tools. So it's not an add-on to DB2 technology. It's the same old DB2 technology. Moving on to the next slide, we can see IBM has introduced a single registry parameter DB2 workload equals to analytics in order to convert the database suitable for analytical workload. So with the setting of a single parameter, a lot of things are automated. Say we have memory parameters, workload management, storage attributes, all are automated. And in DB2 10.5, IBM has introduced a brand new utility called DB2 Convert. With the help of this utility, we can convert our traditional row organized tables to column organized tables. And if you want to know, like, what are the tables which we should convert in order to gain some performance, so we can make use of a tool, Optim tool, known as Optim Query Workload Tuner. It will help us to identify the tables which can be converted to column organized tables, and also it will tell us the percentage of performance that we can improve after converting it to column organized tables. Moving on to the next big idea, it's compute friendly encoding and compression. The second big idea pertains to how DB2 encodes and compresses data and the way it packs the CPU registers. We call it actionable compression, but it is also known as delayed materialization or late materialization. It uses so many compression algorithms, out of which one important compression algorithm is Huffman encoding. Huffman encoding looks for the symbols that occur most frequently and gives them a sort of representation. You can think of it like this way: something that is appearing many times, that should be compressed more than other things that is occurring very less often. Let's take an example. We have a table called employee, where we are storing the employee details, say employee name, employee ID, year of joining. So we see that in employee name, the name Sumit has been repeated many number of times. So what it will do, it will assign a fewer number of bits, let's say 0 to Sumit. So the idea is it will assign a less number of bits to the value which is occurring very frequently in the table or very frequently in the column. And one of the important point to note here is it's dynamic in nature. This is something that a major competitor's technology cannot do. That technology is DBA requires to drop and manually redefine the compression matrix to adapt to new data. The important point is that BLU acceleration can dynamically alter the compression bias using the adaptive compression for new data loads that changes the distribution of common symbols, and thereby it ensures continuous optimization. Now the another algorithm that is used in BLU acceleration is offset coding. Offset coding, it's very useful with the numeric data or the kind of data that we use in financial applications. Let's take an example. Let's say we have an employee table where we store the bonus given to each and every employee. So we see that it varies from the range 3000 to 3200. So what DB2 will do, it will store 3000 as the base value, and then it will offset the remaining value. Say another employee gets $3,050 as a bonus. So it will store only 50. So this is the way it stores numeric data. Now one important point to note that the values in BLU acceleration compression dictionary, these are ordered. Let's assume the value 3200. It compresses to like 10, and for 3000 it uses 01. So we can see that these two values are ordered. 01 is less than 10 as 3000 is less than 3200. So as a result, DB2 can perform a lot of predicate evaluations without decompressing the value. Let's say we have a query where we want to use select star from employee table where bonus less than 3200. So how it will use? It will simply convert the HUI to select star from employee where bonus less than 10. So in this example, DB2 can filter out the values that are greater than 3000 and less than 3200. So here we can see DB2 has to decompress only the qualifying rows, and this is a tremendous performance boost. Now BLU acceleration takes the symbols bits and packs them as tightly as possible into the width of the CPU register. So when we sum up all of the idea components in this section, it will lead to the better I/O because the data is smaller, which leads to more density in the RAM, optimized storage, and more efficient CPU. Because we are operating on the data without decompressing it, and this leads to CPU usage reduction. And in another way, we can say that we are gaining in terms of performance. Now moving on to the next slide. The next big idea is multiply the power of CPU. The third big idea is leading edge CPU technology found in today's modern core processor. that is called SIMD, single instruction multiple data. SIMD instructions are nothing but low-level CPU instructions that enable us to perform the same operation on multiple data points at the same time. It automatically detects and senses the environment and dynamically optimizes the runtime accordingly. So we don't need to do anything. DB2 will automatically senses the number of cores, or it automatically senses whether the processor is SIMD enabled or not. It can put 128 bits into a SIMD register and evaluate all of the data with a single instruction. And this is why this big idea is so important. Being able to compress the data as much as possible, compress the most commonly occurring data, and then optimally pack it at register bits. This reveals the synergy that lies at the core of the DB2 BLU. Now, moving on to the next slide, the next big idea is code-friendly parallelism. Code-friendly parallelism is a very powerful idea. DB2 BLU leverages the processing codes that are available on a server. For BLU acceleration, main memory access is too slow. Whenever we say that the main memory access is slow, we compare this with the access to CPU cache. BLU acceleration is designed to access data on disk very rarely, access RAM occasionally, and do the most of the processing from data and instructions that reside in the CPU cache. So we don't want to retrieve the data from disk again and again. It recognizes the servers that have increasingly larger number of cores, and it is designed to take advantage of the code automatically, so that it can always derive multi-core parallelism for all the queries that we run. Moving on to the next slide, the column store. When we say column store, we mean that a single page in the database stores the values of just a single column, which means that whenever the database engine performs I/O to retrieve the data, it just performs I/O for only the columns that satisfy the query. As in case of traditional database, we used to retrieve the entire row, that is all the set of columns. But here in the case of columnar store, we are only bringing the pages into memory that are mentioned in the query, or that satisfies the query. Here we are directly working on the columns. By using the column store with encoding, DB2 is able to get an additional level of compression, due to which I/O has been reduced. It is able to perform predicate evaluation against the compressed data by using late materialization capabilities. So with the use of columnar store, we can see that the I/O has been reduced a lot. Now we are only interested to fetch the pages related to the particular column, due to which we can put more and more data into the memory as well as in the CPU. Moving on to the next slide. DB2 uses a scan-friendly algorithm for memory caching. So at the first point, For columnar store, we retrieve a page which contains the column. But when we need to fetch hundreds and thousands of pages, and when we'll put it into the buffer pools, we use this algorithm, we use a term called interesting pages, which we use to flag it on, and we use to keep it in the RAM rather than flushing it off. So this is some kind of smarter algorithms that we use in DB2 BLU. Also here we can see that the data can be larger than RAM. Here we don't have the rigid requirement that the entire data has fit into memory. We just need to use the optimal caching. Now moving on to the next slide, that is data skipping. DB2 is able to skip the data that is of no interest to our active query workload. For example, if a query was to calculate the sum of last month's sales, we don't need to look at any data that is older than the last month. So with this technology, DB2 can automatically skip the non-qualifying data, and it implements this data skipping with the use of synopsis table that is automatically created for all the column organized tables. And in this table, it stores the min-max value of each and of the data values of type numeric, or we can say the date time. Let's say in table we have employee bonus. So it will store the minimum and maximum value of the bonus stored in a single page. So this is a way we try to skip the data. Let's say we are only interested in 2014 data. So we'll not look for the data that belongs to the previous year. We have a synopsis table which will point that 2014 data resides in this particular page. So we will only be interested in fetching those pages to the buffer pools. So this is how DB2 BLU implements data skipping. Now moving on to the next slide, we see how DB2 with BLU acceleration, it improves the performance, or it gets the performance boost when these big ideas come together and implement in a single use case. Let's take an example. Let's take the scenario where we have a 32 cores of processor, and we have a 10 terabyte table with a relatively wide number of columns, say 100 columns, and it stores 10 years of data. Now the database stores 10 terabytes of raw data, and the analyst is willing to execute the query. Select count star from my table where year equals to 2010. So we can see here, currently we have 10 terabytes of data, 10 terabytes of raw data. Now, assuming that we are getting 10x compression, the effective data volume comes down to 1 terabyte. Now, since we have 100 columns in the table and we are interested in a single column, year equals to 2010. Now we have 100 columns in the table, and we are interested in a single column. So we will be fetching only the pages that belongs to a particular column. So we divide it by 100, and the effective data volume comes down to 10 GB. Now when we implement data skipping, that is, we are interested in a particular year out of 10 years of data, so the effective data comes down to 1 GB. Now we can see that 10 terabytes of data has come down to 1 GB effective data. Now since we have a 32 core processor and DB2 BLU will leverage the parallel core processing, the effective data is slashed now to 32 bits, 32 megabytes. Now it will also make use of SIMD processing, SIMD parallel processing in all the cores. So we can see that the 10 terabyte of data will be slashed down to 8 MB. And it can be fetched in a very, very less time. We can say sub-seconds. It won't require a second to fetch all these data. So the intention of DB2 BLU is that it reduces the active workload. In this diagram, in this example, we can see that we started with the 10 terabyte of data, and now that active workload has reduced to 8 MB. After implementing compression, columnar technologies, data skipping, cross-code parallelism, and all big ideas. So I must say that we should go for BLU. We should try it and see the performance. And that concludes today's session. Here are the references. All the snaps are taken from IDEP presentations, International DB2 User Group. Thanks everybody for joining the session. Now I'm open to questions.